Welcome back, everybody. We're shifting into our next big unit now, which is waves and optics. So a wave, first off, we need to recall the definition for this. A wave is a disturbance that propagates through space. Now, what that means is that some particle or some collection of particles is moved or is changed in some way, and because of their interactions with the surrounding particles will change in the same way. And because of their interactions with other particles, the particles that surround them will change in that same way. I think throwing a rock into the water and watching the ripples spread is a perfect way to visualize this. So we throw a rock in at some point here, and then we see these little waves, these little movements of water that move outward from that in all directions. So if we do multiples of these, or if we see a little, little splashes going on here, we get multiple waves going out from some center point. That's the propagation of that initial disturbance of us throwing a rock in. Now there are several measurements that we make with waves in general, and we'll talk about some of the specific measurements that we can make with certain types of waves as well. The first measurement, though, that we make is the amplitude. The amplitude is the maximum distance away from equilibrium. So for that example with the water and the ripples, if we have a ripple that's 1 centimeter, a 1 centimeter bump upward on the surface of the water, then that wave has an amplitude of 1 centimeter. For amplitude, we use the variable a if we need to write this out like in an equation. The amplitude, it turns out, doesn't show up much in equations. It influences energy, but it's not something that determines frequency or wavelength or period or the speed. And so it's really not very closely tied with the other measurements. So there just aren't that many equations that we would use A for. And then the units we'd use for amplitude, it's a distance, so we use meters. The period, the time to complete one cycle, so if we watch some wave going by, we should have a high point and a low point in one complete cycle. And we want that water level, or whatever this thing is, to return back to its starting position, its starting situation, before we stop our timer. So the period, we use a capital T for, just like we did with harmonic motion. And then, again, just like harmonic motion, the units on this are seconds. And then frequency, the number of waves per unit time, we use a lowercase f for that, and the units here are hertz. And it's worth remembering that frequency and period are inverses of each other. So frequency is 1 over t, and t is 1 over f. So again, that was all stuff that we did with the simple harmonic motion, but it's been a little while since then. So let's say now we were watching, maybe we were sitting on the dock by the ocean and watching these waves come in, and maybe just kind of tracking the height of the water on one of the posts that goes into the sand from the dock. And let's say that for this one particular wave that we're watching, we start watching it at a position of 0 there. We'll call that our equilibrium. That's kind of the average position of the water, or where the water would be if there were no waves. And let's say that it does something like this. So we plot a graph of position versus time for this thing, and we get something that looks like this. So filling in between the dots. There we go. So given a graph like that, you need to be able to figure out what the amplitude, what the frequency, and what the period of this wave would be. So amplitude is going to be the maximum height or the maximum depression from equilibrium. So that's the distance from 0 to this position, or from 0 to this position. So we can just measure that right here. And we get that our amplitude on that is 0.5 meters. The period is the time before our wave starts to repeat. So if we watch our wave here, we go starting at 0 up to a high point and then down back to 0. And you might think, oh, okay, well, it's back at 0, it's repeating. But keep in mind it has to go below 0 as well. So it doesn't start repeating until after 4 seconds. So we have a bump up and then a bump down, and then a bump up and a bump down. So this section is the same as this section. So our period, we measure from here to here, and that's going to be equal to, whoops, from here to here, there we go. And that's going to be equal to, it looks like 4 seconds on this one. And then the frequency we calculate by doing 1 over the period, 1 over 4 seconds, which would be 0.25 hertz. The other thing we need to be able to do is apply the equation that we typically call the wave equation. Even though there are lots of equations we use with waves, this one is the wave equation. And that's just that speed of a wave is equal to its frequency times its wavelength. And wavelength is a measurement that we haven't talked about in this section before, but we did in our previous class together. Anyway, our wavelength, this is the distance, not the time, but the distance, horizontal distance in the case of these water waves, the distance before a wave starts to repeat. And that'll be in meters. So if I'm looking from the side and I take a picture of the waves on the ocean here, so they have something like this. So this is a still frame. This isn't a graph of motion versus time. This is just a picture of some moment in time. So here I could measure the amplitude again. But I don't have time on my my x-axis, so I can't measure the period or the frequency using this graph. But I can measure the wavelength. So if I start, say, right here at a high point, our wave repeats after we go all the way down to a low point and then come all the way back up to a high point. And then this section is exactly the same as this section was. So our wavelength is going to be like this. And then that'll be measured in meters. And it turns out that the speed is equal to the frequency times the wavelength. So maybe we have, say, sound waves. Sound waves travel at 340 meters per second. And maybe I hear a wave that has a frequency of, say, 200 hertz. 200 hertz. That's a pretty, that's like a human speech pitch sound. And then that's times the wavelength. We want to figure out what the wavelength is here, so we'll divide both sides by the 200. Hertz, remember, is the same as per seconds. So 340 meters per second divided by 200 per seconds is equal to our wavelength. And so here we get our wavelength is just equal to 1.7, and then the meters, meters per second divided by 1 over seconds, we can treat that as multiplying by the reciprocal, so meters divided by seconds times seconds over 1, and so we end up just with meters for our unit there. So 1.7 meters between high points or low points on that sound wave.